Hello, this is Bryant Myers, and welcome to another episode of Debunking Flat Earth. And we have part 6 tonight in this debate review series with Austin Witsit, because there's just so much good stuff that came from that. And tonight I got Black Swan number 2 for you. And in the last little live stream with MC Toon and I, we did the Black Swan, well, I'm going to call it Black Swan number 1, which is basically applying Coulomb's law to this incoherent dielectric acceleration model of downward acceleration that certain flat Earth sort of sects have, the Globebusters group being one of them. So in this video, we're going to go through Black Swan number 2, which relates to that, as we'll see, to Coulomb's law when we divide by a dielectric. And we're going to specifically talk about the Faraday cage. And as before, I want to start with a nice little video clip or soundbite from Austin so we can hear his position in his own words.
Wait, time out. You said gravity can't be shielded. You know electrostatics can't be shielded or removed.
That's
it's all
right. Provably.
Are you saying that we can shield electrostatics?
Electric fields, yes.
Electrostatics.
Electrostatics, if you have an electrostatics object, it's giving off an electric field. That's how it works.
There's an electrostatic field. But can you ever shield from electrostatics?
Yes, you can. You can shield electric fields.
You can't, Bryant.
Well, show me the paper that says that, please.
Okay.
I'd love to see that evidence.
You're making the positive claim that you actually can do it. So what, you use a Faraday cage? That doesn't do it. So what else are you going to use other than a Faraday cage?
Look up any electrodynamics textbook. Electric fields can provably be shielded. Provably.
You cannot eliminate the variable of electrostatics, and you can't block them. Faraday cages stop electromagnetic transfer, not electrostatics.
Okay, so any electrical engineer or anybody that's into, electricians, or if they were watching that, would have been cringing, because you absolutely can shield electrostatics. In fact, this little image here, we've all seen these Tesla coil type of demonstrations where someone's standing, even sometimes kids, in this cage because it's so safe, because they know that these electrostatic fields can be shielded, and they're absolutely fine. Now, if electrostatics could not be shielded, these people would be getting electrocuted. And we're going to kind of go through in this video how these Faraday cages work. But the point is there was many mistakes, what you just heard from Austin. There's actually more than one mistake. First, he said that electrostatics can't be shielded, and they can. And then he said that if Faraday cages can't do it. Well, absolutely, that's actually what can do it. Towards the end of it, he said that electromagnetic fields can sometimes be shielded, but not electrostatics. And it's like, well, it's a little bit the other way around. Actually, as we'll see, when you get into really high frequency electromagnetic waves, then you lose a little bit of the shielding there. But pure electrostatics with a static or constant electric field is 100% shielded from a Faraday cage and from a Faraday. And we'll talk about the proper definition of that in this video. So we're all kind of familiar with these Faraday cages. And I don't know if you knew this, but in your car, if you were struck by lightning while you were sitting in your car, you're going to be safe because the metal of the car is creating a Faraday cage around your body and keeping you safe. So all the electric charge and all the electrostatics is just surrounded by the surface of the car, and then it eventually gets grounded. And we'll see how that works here in a minute. And if electrostatics didn't shield, or if you couldn't shield electrostatics, then these people that work on high voltage lines that wear Faraday suits, then if they couldn't be shielded, their lives could be at stake here. But absolutely, these suits do work because they're highly conductive, and they do shield electric fields. So what is a Faraday cage? So by definition, a Faraday cage is some enclosure that's surrounded by a conductive material, usually a screen. This is why when we think of Faraday cage, we think of a cage because of the screen that's around it. But as we'll see, this is not really the proper definition, and it's not the way to actually even make the best type of Faraday cages, which I think is one of not only Witsit's misunderstandings, but also Gleam kind of going through some of his stuff. And actually, we'll get to Gleam's questions tomorrow, so stay tuned for that. So what he did was he created a foil-lined room, and then he had a very powerful electrostatic generator outside the room. And he used an electroscope to measure that there was no electric fields inside the room when it was surrounded by this conductive sort of foil. And so this is where the name Faraday cage come from. So he's the first one that kind of did these experiments to see that there is no electric field inside of a Faraday cage. So in this first image here, you can see a Faraday cage in the absence of an electric field. Then the charged particles in the wall of the Faraday cage respond to the applied electric field. So you have the negative moving towards the positive side, and then the positive saying over towards the negative. Typically, it's the mobile electrons that are moving. And then due to all this, the electric fields cancel out inside because the electrons are neutralizing the positive side, and on the negative side, you have the positive charge neutralizing the negative side. So in essentially what's happening is that these electrons are mobilizing to one side and then the positive charge on the other to exactly cancel out the electric field. And it has to do with metals being, again, a conductor is where you have mobile electrons, is that it's because of the electrons are mobile that they can move and respond to the electric field. And this is all explained by Gauss's law, which is basically saying the flux, which is the electric field times the area, so it's pretty much the density of the electric field, how much electric field is flowing through an object, is equal to, it's an integral when you integrate the area times the electric field, but it's essentially area times electric field if you have a constant area. And that's going to be equal to Q enclosed over epsilon naught. So it's essentially saying it's whatever charges are inside the Gaussian surface, you know, a word that Witsit loves to use, when you draw any Gaussian surface, and if there's no charge inside the Gaussian surface, because I didn't mention this, all the charges on the surface, when you apply an electric field, they end up all being on the surface. And that has to do, if you actually solve some of these equations, you'll see that if the charge density is spread out through the volume versus the surface, you have a minimum energy when it's spread out on the surface. So again, nature kind of goes towards this minimizing energy kind of equilibrium. And so this is why all the charges always stay on the surface. And this is why you're safe inside your car, you're safe inside a Faraday cage, and you're safe inside, you saw that suit. Because the electrons are staying on the surface of the conductor. They won't go within the conductor itself. The gist here, when we apply Gauss's law, again, Gauss's law is literally telling us that the electric fields are zero inside a conductor. The electric fields are zero inside a Faraday cage. A perfect, we'll talk about what a perfect Faraday cage is in principle. It's essentially a solid conductor with a hollowed out interior. So it's not a mesh or a screen. Because if you got little holes in the Faraday cage, you know, it's possible that some, typically not electric field, but if you have a time varying electric field or an electromagnetic wave, they typically get through. But even a little bit might get through with a pure electrostatic field if you have a screen. But we're talking about so many decimal places, it's so ridiculously small that it's hardly measurable. But when you have a solid Faraday cage, that's a solid conductor with a hollowed out interior, 100% of the electric fields are shielded. So Witsit, you are wrong. And we'll see why this is a black swan here in a minute. So, and again, as I was saying, here's your Gaussian surface. So it doesn't even matter how you draw the Gaussian surface. Basically, it's just saying that it just makes the integral more difficult when you make a weird shape like this. But you can still do it, and because there's no charge inside, because again, I said all the charge on the outside of the conductor, the Q enclosed is going to be zero. And because the Q enclosed is zero, the electric field is zero. And because the electric field is zero, there is no, again, we're talking about an applied electric field on the outside. So this is 100% shielding when you have a solid Faraday cage that's got just a solid metal without any holes in it. And again, Witsit loves his Gaussian surfaces here. Well, unfortunately, his Gaussian surface is a demise of his model, because you draw a Gaussian surface inside a conductor around applied electric field, you're going to see that electric fields are zero, which means if this was, and this is kind of a little giving away the black swan here, but if electrostatics is a source of gravity, then we should be levitating inside a Faraday cage. Because it's provably shielding 100%. And again, Witsit says over and over again, it's all electrostatics. So again, I think the confusion in the debate when you saw that little video clip of us going back and forth, I think Witsit is trying to think of a Faraday cage that's got like holes in it, which again, they're very, very good at shielding electric fields. I mean, if you do have anything left inside, it's 0.000000. I mean, many zeros out. So it's not very much. But you might still have a little bit of electric field inside. But if this was solid, a solid room, and we're going to see this in a minute here, then all bets are off. You're getting 100% shielding. Okay, so here we go. This right here is a Series 81 RF shielded enclosure. Now, this is a tight, holeless, seamless, solid shell Faraday cage that will 100% all electrostatic fields. Guaranteed, 100%. There are no static electric fields that are going to get in here. So again, a holeless, seamless cage, and this is not really a cage, it's more of just an enclosure that's surrounded by a conductor, and it has plenty of thickness. You're going to also get shielding of radio wave frequencies and electromagnetic waves very, very well. Actually, the only thing this room doesn't shield is low frequency magnetic fields. Magnetic fields are really hard to shield because there's no magnetic monopoles, where electric fields come from positive and negative charges, so you can surround a positive charge by a negatively charged medium, and you can surround a negative charge by something positive. So you definitely can shield charges in electric fields because there are electric monopoles, but magnetic monopoles there aren't. So every magnetic field is wrapping around, so it just makes it much harder to shield. Now here's like a little performance curve of this S81, this enclosure, and you'll see that right here, this red line, the only thing that this is not shielding is very low frequency magnetic fields. But up here now, when it says a dB of 110, what this means is dB is a measure of the attenuation of the electromagnetic field. So whatever the intensity is outside the enclosure, inside of it is you can measure the inside and see how much it's attenuated. And the dB is a logarithmic scale now. So a dB of 50 is not just 10 points higher than a dB of 40. It's actually 10 times higher. So when you have a dB of 110, in fact, they consider 90 to 120 as the best of the best shielding type of. If you can get a dB of 90 to 120, you are at the upper echelon of shielding electromagnetic fields as far as the Faraday cage technologies go. And this device that I showed you absolutely is at that standard. But here's the thing. For static electric fields, you don't even need this performance chart because it 100% shields electric fields or electrostatic fields. And again, Witsit, Globebusters, those guys, they're saying it's all electrostatics. They're not saying electromagnetic waves cause gravity. They're saying electrostatics. And again, this is why it's Black Swan number 2, because these Faraday cages will 100%. Witsit is just wrong. And in Gleam, who also, we're going to go through Gleam's questions tomorrow, which is going to be a lot of fun, so stay tuned for that, also says the same thing. And they are just provably wrong. And I'll show you in a minute how we can prove that they're wrong, which is not too hard. I just kind of wanted to mention here that that room that you saw, this is kind of one of the standard best, the one I showed you. There are many companies selling a version of that with their sticker on it. So it's one manufacturing company that's making these really, really, really high quality Faraday cage type of rooms. So there's many applications. So there's literally hundreds and hundreds of these rooms I just showed you out there. And so this is why it's living proof that gravity is not due to electrostatics, or the downward acceleration is not due to electrostatics, because all these people that were working in these rooms would be levitating because it 100% blocks the electrostatic field. And again, it's used in meteorology, it's used in magnetic resonance and different medical sort of hospital situations where you got to block all the electromagnetic fields, bioengineering labs, wireless product testing, secure computer rooms, high voltage test labs. They actually make these too for the protection from a possible EM pulse type of, if that ever got out there and countries tried to shut down another country with EM pulses, a lot of sensitive type of things are surrounded by these very powerful shielding rooms, which would protect from an EM pulse. And you can see the applications here. So there's hundreds of these rooms that are out there. And if you really wanted to test, so here we go. I picked this one specifically, this Keithley electrometer, because it's referenced in thousands of research papers. This is like an industry standard high-level electrometer. So this will measure the Earth's electric field, the 100 volt per meter type of drop-off, which, again, it drops off very quickly, much more than gravity, as we talked about. But it will measure that electric field of the Earth, but it will also measure, if you took this meter inside of one of these chambers, you would see the electrostatic field is 0 to pretty much as many decimal places as this device had. Now, if you applied an electromagnetic field that had electric and magnetic components, then, as you saw from the performance chart, a teeny tiny bit would come through, not much. And only if you had really low frequency magnetic fields would you notice any appreciable numbers here. So we can test this. We can see that provably these type of Faraday cages, especially the ones that are seamless, that don't have any holes, that are solid conductive material, provably have 0.0000000. You can go out as far as you want, electric field. And this literally is Black Swan number 2. This debunks the whole incoherent dielectric acceleration, because we can prove that electric fields are shielded, and gravity, by the way, gravimeters, which MC Toon, we talked about that the other night, those go, the absolute gravimeters will go 9 digits of accuracy. And they use Faraday cage type of, in the absolute gravimeters, there's a Faraday cage kind of built into it. So it absolutely is shielding electric fields. But if you took a gravimeter inside one of these chambers that blocks out all electrostatic fields, you would still measure the same gravitational field. These things do not shield gravity. Gravity cannot be shielded. So here we go. This is kind of the mathematical form of both Black Swan. So remember in the last little talk with MC Toon, we use Coulomb's law, and here's my little, I've still got it here. Here's my little Black Swan. And we basically use the electric field formulation of Coulomb's law to show that it is literally impossible for the downward acceleration to be due to Coulomb's law, because Coulomb's law depends on both charge and directly proportional to charge, inversely proportional to mass. And so it absolutely is an utter fail, where gravity is constant because inertial mass balances or cancels out gravitational mass. So we use Coulomb's law for Black Swan number 1. And now for Black Swan number 2, see over here, and we did talk about this the other night, but I just kind of wanted to put it into kind of formalized terms. So now we're adding the dielectric. So it is the greatest of ironies that they call it incoherent dielectric acceleration, because the dielectric part of it is literally Black Swan number 2, because it shows you that electric fields can be shielded, and the only places they're not shielded are in air. Well, even in air, it's shielded a little bit, in a vacuum. But you start to get into materials, water and all these different solids. Certainly, well, I'll get to conductors in a minute, but even non-conductors are shielding electric fields to varying degrees. And even though they're not shielding them 100%, this is what Witsit wasn't getting. Even if the Faraday cages, again, just taking his line of reasoning, saying, oh, they can't completely shield electrostatics. Well, it doesn't matter if they're shielding even 50%. Gravity's not shielded at all. You're not helping your case by admitting that it might be shielded a little bit, because gravity is shielded not at all. So he absolutely debunked himself within our exchange there in many ways. So now here's the thing I kind of brought up with MC is that conductors have a dielectric of infinity. That is to say that the Coulomb's law is an electrostatic force. So when you have a pure conductor, you are adding infinity here, so you're getting the 0. So you get electric field is 0, the force is 0. So nothing is happening inside of these really well-built Faraday enclosures or Faraday cages. And if that was the case, then we would be levitating inside, because if it is shielding out the electric field or electrostatics, and if, as Witsit and Globebusters and these people that describe this electric gravity model say that a downward acceleration is due to electrostatics, if we can prove in these rooms, which we can, that the electric field is 0, this debunks your model, totally annihilates it, destroys it. You've got nothing. You really got nothing. So And again, these are, I challenge you guys to prove me wrong here. Show me a study that will say that electric fields can't be shielding. I mean, good luck with that. I mean, we know they can be shielded, and we can use the very, as I mentioned, the very sensitive electrometers to measure that there's no electric field inside of a Faraday cage. Where gravity, we can use gravimeters to show that gravity is not shielded. It can't be. So this is a black swan. Number two, I mean, we're killing their model in many ways, but this is a very definitive black swan for incoherent dielectric acceleration. May you rest in peace. You had a good run, but it's over. Incoherent dielectric acceleration is a dead model. It fails, provably, in many ways. And I hope everybody that's on the fence can take this to heart and see how nonsensical some of these flat earth science or explanations are and how they contradict themselves in so many ways. And just be open-minded to see the truth, the real truth behind it all. And again, hope you enjoyed this video. Please do like and subscribe my video. Tomorrow, we're going to have some fun tomorrow, because now we're going to go through that pinned comments or questions by Gleam. And I've answered them all. I just wanted to do this today because it dawned on me, going through Gleam's questions, that this is a definitive black swan with Faraday cages. And but that'll be fun. And I'm going to go through some of their electric universe papers too. And we're just going to debunk the hell out of all of it. It's going to be a lot of fun. So thanks again. Do like and subscribe, and have a wonderful evening.